If you have any differential amount of current, you want the differential force, you can get that. Now, if you integrated that differential force over where the wire existed or wherever it was, then you would get the total force on the wire or whatever. Another law just like this is for a current element. If you have a charge, Q, moving at a velocity v, it's like a current, right? Charge moving, and it's in the presence of a B field. There's going to be a force acting on that charge. This is the actual force acting on the charge. This is the magnetic force, and it's going to be equal to QV cross B. These are both absolutely true. Y'all with me? How many remember this from physics? Now, a lot of times what they'll do is say if you have a charged particle, Q, and it's in the presence of both an electric field and a magnetic field, then the actual force on this, it's going to act, I'm just drawing it this way, the force on the charge will be equal to Q, and then they'll have V cross B plus E. Now that's the total force from both the magnetic and electric field. Y'all follow me, class? I'm just trying to show you this. The really important thing to note is this magnetic force is always perpendicular to the velocity vector. Let me be real clear about this. So suppose I had a velocity vector, or the velocity like this. I have a charge, Q, that's moving with a velocity in that direction. Y'all with me? And then I have a magnetic field coming into the board. So I'm going to have a magnetic field into the board that's just some B naught. And it doesn't, I'm not trying to put too much emphasis on direction. Y'all following on this? So if you look at the force on this, that's equal to magnetic force, QV cross B. All right, V cross B is a force upward. Do you all see that? Now, that would be the direction of the force. If it moves a little, please watch this, this is important. If it moves a little, well, that force is going to cause us to bend upward. Do you all agree with that? So if it moves up, then it cannot gain energy or lose energy because this magnetic field is always perpendicular to the velocity. Y'all follow me on that? That's real important. It can't accelerate it or decelerate it. An electric field can. So if it moves a little bit, then the force, if it's going in this direction, let's assume it gets a little upward trajectory because that's the direction of the force, then QV cross B is this way. And what I'm getting at is if you look at the magnetic force acting on a charged particle and there were no other collisions or anything like that, and it was free to move, forget gravity from it, it would just move around in a circle. Do y'all follow me? You remember that? That's called a magnetic bottling effect. So let's talk about the radius it would move in. We're going to use two things. I'm going to assume that I have a B field that's going to be into the board. And it's the same everywhere. So I have a B field that would be in Webers per meter squared. And now I'm going to say this is the actual charge and it's moving this way with velocity V. And I know that there's some radius that's going to move around. It's going to keep going no matter where it is. This radius will be the same. It's just going to go around the circle. Can you all follow me on this? It will be. So what is the thing that's really limiting that radius? Well, do you remember if you have this charge and it's got a mass m, all right, that there's an acceleration of gravity. And the gravitational acceleration will cause a force m, and it would be v squared over r. You all remember that? V squared over r was what? It's the acceleration for an orbital body. Like if you take say a lead weight on a string and you rotate it around. The acceleration at the end of that weight, which will be a force, v squared over r is the acceleration times the mass is the force pushing that thing that's trying to break the string. Do y'all follow me? But this magnetic force is holding it in. So what they do is they equate the magnetic to the electric force, and I'm going to do it right here. Because the radius isn't changing, so they get m times v squared over the radius, this is the radius right here, the radius that this thing's moving in, will be equal to qv cross b. And here's the way they do it. They're assuming the cross product is just going to be equal to the magnitudes first second because I've put the magnetic field perpendicular to the velocity vector. Do y'all follow me in this class? So now I get this. I get m times v squared over r is equal to q times magnitude of v times magnitude of b. What I'm about to show you something is very important. It's called mass spectrometry. It's for mass spectrometers. They use this to differentiate charge-mass ratios, and they'll have different grids that catch these things so they can tell the charge-to-mass ratio when they have a gas and they electrify, and they can therefore know what the gas is. Basically know what the constituent parameters are because the charge-to-mass ratios for single ionizations, for all the stuff just about out there is very well known. So if you look at this, what you find out is this radius. Let's just reduce the complexity here. If you go ahead and take a look at this, maybe I'll go right here so everybody can see it easier. If you look at this, I got mv squared over r is equal to q times v cross, or qv, just qv times magnitude of v. So I'm going to get rid of one of these v's. Right. And this is a velocity, by the way. And this is a radius. Maybe I should use r. And if I wanted the radius, multiply both sides by r, I'd go ahead and I would get the radius itself is equal to m times v over q divided by b. Y'all agree with that? Now, something to take from this, the larger the magnetic field, the smaller the radius. The smaller the mass, or I should say the ratio of mass to charge, as it gets smaller, the radius goes down. And that velocity becomes something very interesting. Now, here's how they do it in a mass spec machine without getting into all the details. How many know what a mass spectrometer is? Have you heard of these things? They use them in gas chromatography. Anytime you got something, you're trying to figure out what the gas is made of. They have something where they get single ionization, and they can do this, and then they accelerate. You could probably do this with solids too. What they're going to do is this. They'll have something where they have, do you know what a vacuum tube is, everybody? Or not? Do you know what I'm talking about? That was prior to the transistor, right? A vacuum tube is something where it's at a very low pressure, and you have sets of grids. Really, we just use a triode. And what they do is have a cathode here, and they have a hot filament here. All right? And then they're going to put, this is inside, this is a hot filament right here. And this is a cathode. It catches this thing. This is a vacuum in here. It's actually close to a vacuum. But what happens is this cathode gets really hot. It'll glow red. It's called thermionic emission. It'll emit electrons, right? Electrons from there. Now, this plate will have a certain potential on it, a plus V. It'll accelerate through. Some of them will hit the plate, but most of them will pass right through because it's porous and hit the cathode. That's where the ground is. Do y'all follow me on this? Now, that is something where it's accelerating charge into that. But the voltage difference between here and the cathode will really limit the amount of velocity those electrons can take, all right? Because it's really an integration of force. It's really the voltage times the charge will be the actual energy that's going to be absorbed by that. If you remember, the integral V dot dl is going to be the voltage. But if you think about the force, it's QE, right? QE integrated from one point to another is really going to be QE times the voltage. So the actual energy it gets would be Q times V, would be the amount of energy, and that would be equal to 1/2 mv squared, so you can figure out the velocity from that. I'm trying to be real simple about that. Does that make sense to everybody? So over here, what they do with the mass spec, I'll show you here. Remember, that's the radius. This is a little more involved than I'm making it, but it's basically this. They're going to have a set of, they're going to have this thin tube, and here they're going to introduce an ionized molecule. So they can ionize these things in a lot of ways. You all know that you basically, if you just have a large voltage difference between 2 points, then you have the grid where it's interleaved, plus, minus, plus, minus, plus, minus, and you throw something through there. It's almost like that stuff they zap bugs with outside, where you've got something that you'll zap basically every time a bug goes through. Here it's similar with the grid, like that. It comes through, it ionizes the particles, and they're really going to be something with usually a single ionization level, almost always. So it's going to have a given mass to this particle and a given charge Q, usually just one electron distributed. Then it's going to go through and accelerate through a set of grids here, porous grids, and it's going to have a certain potential difference. Dr. Whitmer's book doesn't show that. Now, they come in here, they know the velocity of things moving at when it gets in here. Can everybody follow me on this? Or the amount of energy, at least. Y'all with me? Now it comes in here, and here's where the mass spec is. And comes in, and basically the B field will deflect all this stuff to different grids. All right. And these grids have a current meter on them, and they can detect the amount of current there. And by virtue of the fact where this thing's, the radius of this thing, you know, this is part of a circular arc, the radius of that thing determines the actual mass to charge ratio. And these grids are nothing more than things that catch the actual charged particles, and they can figure out what elements are there. You should read about this. It's kind of interesting. It's a clever way, but the requirement is this has to be very low pressure. You can't have any meaningful collisions in the length that these things travel, or else the whole thing breaks down. You also need a fairly strong magnetic field. Do you know what a magnetron is? You guys, you know. Cavity magnetron is the reason radar worked in World War II. It was critical. And I'm not going to talk about that yet, but all these things with large magnetic fields are used to either create energy at a certain frequency or separate charge, mass type things and be able to determine what in fact is there. It's a very interesting thing. If you do any kind of gas phase chemistry, the mass spec is really the thing you use more probably than any other item. Now that, I'm just showing you this. This is in his book. He doesn't have anything that's really confusing. Something else about this environment was single charge particles. You know what the aurora borealis is? In your own words, what is it? Just tell me. Anybody?
It's like solar wind bouncing off like Earth's magnetosphere.
Okay. The aurora borealis, or the southern hemisphere's glow discharge, is really when charged particles from the sun come in, and the magnetic field lines guide them down, and they'll spiral down the magnetic field lines. Then they'll come in contact with the atmosphere and ionize it, and you'll get this glow discharge. It's really like a fluorescent lamp kind of tube. So if you think of the Earth, you should know this at least in the general sense. And this is the North Pole and the South Pole. They're not vertical, by the way. It's tilted, but I'm just showing you. So the magnetic field of the Earth, and the way this works is when you get this thing spinning, the Earth's got a molten core of iron, and there is a ferrous component to it. So when it spins, it generates a magnetic field like this. It's a current kind of deal. And if this is the magnetic field, one thing you'll see is the magnetic field, assuming it's aligned this way, straight up. If a charged particle is coming in straight down here, remember it's QV cross V. So if a charged particle is coming straight down here, it doesn't bend. You all follow me on that? But if it's trying to come in this way, well, QV crossed into the B field would deflect it. You all follow me? And it would lose its energy out there further away. That's the reason we're not dead, by the way. It's because we have a magnetic field on the Earth, and it prevents these high energy particles from getting in. If you think about it like so, you got QV, right? QV crossed into B, and if B's up or down, it's going to deflect these things into an orbit there. It's going to trap them, is basically it. The only place it doesn't trap is if they're coming straight down here. Now here's what really happens. Suppose you have you have highly charged particles moving in here. They'll hit this field line and they'll just rotate around it and come down. And actually, as they get closer and closer to the Earth's center, or to the Earth, the magnetic field gets stronger, so the radius becomes smaller and smaller. Do you know what a whistler is? Anybody ever heard of that? You know ham radio, guys? If you listen to ham radio, and it depends, there has to be a solar event. What you'll hear is this, on certain frequencies. I've heard this. You'll hear, and what happens is, these charged particles are coming down, and as they're accelerating, they radiate. They radiate frequencies that, for certain, I wish I remembered which ham radio band it was, but I think it's the 10-meter band. You can hear that thing. All right, you can basically, it's AM type of thing, you know. And what happens is they're coming down, they hit a minimal point, and then they are thrown back out and stuff like this. But as they accelerate down those lines, they get closer and closer to a dense Earth environment, and then they start ionizing the actual, really the gas around it, and you'll see through collisions, you'll see this bright aurora. Has anybody ever seen the aurora borealis? It's a greenish kind of eerie glow, and it looks like waves of particles. You'll see the thing that is almost waves. They're called the northern lights. There's one other event like that that happens. It's not related to the sun's particles, and it's called a sprite. Do you know what a sprite is, anybody? I'd be shocked if you did. It has to do with lightning. When there's intense lightning, cloud-to-ground lightning, from the low charge center to the Earth, what happens often, it has to do with the electric field exceeding a threshold for ionization. You'll see this dull greenish blue glow. It's very low. Above that, it's called a sprite, and it's where there's a large level of ionization. That's something else. I've done work with transient electromagnetics related to nuclear weapons and lightning, and that event is an interesting one because it's ionization of really the ionosphere, about 60 kilometers an hour. It's called a sprite if you want to look it up. Okay. So that's the differential force, and to get the total force, we integrate it around a loop. Now I'm going to go through the IDL crossbeam, the classic problems, and I've got another story for you. This one's an interesting story in my opinion. Did we start at 1:15?
Yeah.
How in the world? I didn't think I spent that much time talking. I guess I did. Sorry. This stuff is interesting to me for a lot of reasons.
Have you ever heard of single photon interference?
No. I mean, I may have. What does it mean?
It's more like a phenomenon where they take a single photon and it's the split experiment where they put it through a split window and it creates a frequency that we thought would be random, but it comes out to be
a single photon?
Yes, sir.
If you break anything up that's a photon into more than one particle, it's not a single photon. Or more than one energy.
I don't know all of it, but when I looked into it, it's like if you were to send like multiple beams of light through a split window, they would.
Talking about thin slit diffraction in physics. That's yeah. I think I know where you're going with this. It basically verifies the quantum behavior of light, and light is both a particle in a lot of ways as well as a wave, and it also behaves with quantum properties and probabilistic scatterings, I should say. Okay, I'm not going to go there. I want to go to the classic problem. This is one you can prove in a lab very easy. So here's the classic problem. Suppose I have a current I, make it infinitely long, and I have another current at a distance d away, make that infinitely long. Okay? I'm going to call them both the same, and they're both in the same direction. Now this you have to know. So if you look at this, I want you to be careful about this and see. Y'all got the idea. You've got two infinite currents, Now what our goal is, we want to find the force acting per meter on one of these. So what I'm looking for is, first, I want to figure out what the differential force is here. All right? Well, I know, this ain't gonna do it for me. I know that the differential force is going to be IDL cross B. So this differential force right here would be equal to IDL cross B. There it is, right? Let's assume it's in free space. I got a great story related to this. So how do I get what the magnetic field is? And it cannot be the magnetic field caused by this little chunk of current. It's a magnetic field that's external to this. You with me? What is the magnetic field if I've got an infinite line of current? Do you remember? If I just have I infinitely long and I'm a distance rho away. Well, first the H field is what? Do you remember? I said
it's I over 2 pi rho.
I over 2 pi radial distance in the A phi direction, right? Y'all agree with that? Let me give you some coordinates for this one. So I'm going to say this is the x-axis. No, I'm going to make this the x-axis coming out of the board. This is the y, and this is the z-axis, okay? I'm just giving you some coordinates. Call this the origin. Everybody with me? So if I'm out a distance and d away, I can say that the magnetic field here, the H field itself, would be equal to I over 2 pi. In this case, it's d, right? It's just the distance from the actual current the current itself, minimal distance to the point of observation. You all agree with this? Now, it's in the direction phi. Notice my coordinate system. There's z. So phi here would be in what direction? Take a look. IDL cross B. I'm right here. Phi's going into the board. It would be minus AX, right? Plus is AX is this way, minus AX. So here it's going to be, and I'm trying to make that a little better, I over 2 pi d, and the minus AX direction would be H. So this H field right here is equal to I over 2 pi d minus AX. Now that's the H field. How do I get the B field, class, if we're in free space? B is equal to mu H, right? Mu itself is mu relative times mu naught. Mu naught equals 4 pi times 10 to the minus 7th henries per meter. If it's free space, mu relative is 1. So I'll just say that now if I want the B field here, it's equal to, technically it's minus mu 0 times I over 2 pi dAx. Do you all agree with that? You got to make sure you see that. And I got it just because I know the distance I am from the center of that wire, right? It causes it. So this current is causing a B field here. That's the B field. You all agree with me?
Yep.
All right, now I want to get the differential force. And I'll do it here. So I know the differential force is equal to IDL. Which way is I going? I made it go up, right? So it's going to be, what is IDL, guys?
IDL.
I times what? DZAZ, right? I'm saying it's going up. So it's I DZAZ because its differential direction is Z. It's crossed into the B field, which is minus mu 0 I over 2 pi d AX, right? What do you notice happening? This is the differential force. Well, I'm going to go ahead and do this. I made them the same I's, but it could be I1 and I2. Do you agree with that, class? I made them the same for simplicity. So it's going to be mu 0 I squared, right, over 2 pi d. Then I have AZ crossed into AX, which is
AY. But
Z crossed into X is AY, right?
there's a negative.
Wait a second.
Yeah, there's a negative on the mu naught. That goes to the negative AY.
That's right. Minus AY. And this would be, by the way, newtons per meter. Y'all follow me? Now, what direction is the force? The differential force is actually in this direction, right? I can make the same argument. The differential force on this one will be in that direction. The wires are pulling together. This is my point. You all with me? The force per meter would be what? Just integrate that over a meter. Do you agree with that? So if I want the force per meter, it's going to be equal to, and it'll be pulling together, it'll be mu 0 I squared over 2 pi d, and I could put minus A1 if I wanted to, and that would be newtons per meter would be the units, that would be the force per meter pulling it around. Now, the force, and it's important to see this, if you have currents in the same direction, they pull together. This is always true. So if you got a current here and a current here, they're called common mode currents, they pull together. What do you think happens if they're in the opposite direction?
They repel.
That's exactly right, they repel. Now here's a story. The problem is I have no way of verifying whether this is true or not. So when I was doing my PhD, my professor was named Les Hale, and he had worked out at Los Alamos, it's a long story in this one, during the actual development of nuclear weapons and all this. I met a guy that was out there at the Manhattan Project named Dr. Foote, who was a physicist, and but he didn't tell me much about what was going on. Anyway, so this is the original nuclear weapon stuff. But when they blow these things up, what happens is, I did a paper related to this. You get this large positive charge, and the electrons that blow away are called Compton electrons, and they cause this massive current. If you ever watch any of the movies about nuclear weapons going off when they have films, you'll see all sorts of lightning and stuff like that around there caused by this. Well, when that happens, all this charge that's blown to kingdom come, in a sense, this negative charge, wants to get back to its parent positive charge. And the way it does, it flows through the path of least impedance, or they say resistance, but it's impedance. So when they blow these things off in the desert, back in, I think, about 1840, 1850, the railroads came through there. And also mines were all over the place. They dug down for silver, gold, things like this, copper mines, and railroads were everywhere. But some of these things are buried with dust and all that stuff. So there's all these rails like this that are underground. So they blow some of these things up, and they go out and do bomb damage assessment. Now, closer to where the bomb occurs, it turns into basically glass. It's quartz, it's fused, all the sand is fused. Has everybody ever seen this stuff or not? I don't think it's classified. But when a real nuclear weapon goes off, you're going to get, if it's over a desert at least, and there's a sizable amount of sand kind of stuff, usually they do in deserts, or you'll get this layer of pseudo-glass, and it'll be molten kind of crap. Once you get a little further on, they have to do all this bomb damage assessment. They have to take a look at the effects in the terrain, see what's going on there. So in doing it, they found something that was unique. And this is just what I've come to understand. I was told this, I forgot how I told the story, but this is one of the unusual things. They found the railroad, the actual rails were pulled off the ties and fused together. Think about the amount of force it would take to do that. So we went through and we calculated, I forgot how much force it takes to shear a railroad, a piece of rail off per meter off of the wood ties that they're on, but they're also buried, so it's even more. But what we did is, we took this, we knew the spacing, the actual spacing is about 3 feet between rails, weather rail. And so we figured out the current that had to be induced by that thing. You're talking about hundreds of kiloamps, actually probably 10 or more mega amps that had to have a sustained value. That's a huge amount of current. So that happened sometime about 1947, 48, 49, somewhere in there. Then they did what's called a Bikini Island test. Does anybody know what this is? Anybody? You've heard of it?
Is that where they nuke it underwater?
No, this is above air. So it was 2,000 miles. These are hydrogen bombs. These are not the firecrackers. These are the big guys. 20 megaton, 30 megaton bombs, or 10 megaton. I mean, the ones that they blew up on Hiroshima and Nagasaki, these are 100 kiloton yield. The other ones are orders of magnitude. They're literally 10 to 20 megatons. So you're talking about 2 orders of magnitude larger. These are hydrogen bombs. So they went out there, the U.S. Navy's out there watching these tests. And remember, this is news. They're not sure really what's going to happen. So they lit it off. It was by the Bikini Islands. You should read about this. And they couldn't communicate with the ships for a long time. The thought was that the ships were destroyed by the nuclear weapon. The ships are a long way off, by the way. So it couldn't have been the immediate blast. That's the thought. Actually, the ionization prevented any kind of electromagnetic communication. The whole place was loaded. The area was basically like in an isolated, it was an electromagnetic shielded area because it's all through there. We finally got through. Now Hawaii is 2,000 miles away, and this is what my professor told me about. Most of the stuff you're not going to see even now. They had a power grid. Now, power grids, pretty hard to just bring down because they're meant to take like lightning, and when lightning hits, it shorts it to ground. But that's a differential mode, plus, minus, going to ground. It's easy to get there. When you have all this, first these Compton electrons are blown all over the Earth, and they're trying to get back, and they're coming over the ocean on the surface. We'll get the skin depth later. And they're coming, and they find this nice long conductors from one side of the island to the other. How do you think they get to one? They get on the conductors, and it destroyed the power grid in Hawaii. This is the first time a lot of this stuff actually happened. That was another shocker. So then a guy named Connie Longmire and a bunch of other people came up with all these nuclear codes. There's the fast time stuff called EMP you hear about that destroys electronics. Then there's the slow time. The slow times, it is scary bad for anything that is a long conductor. Do you know how the solar wind, when they have solar events, it messes with the pipelines from Alaska? Do you know about this? Causes huge corrosion, all the problems that happen, the oil pipelines. Well, this is similar to that, only much, much higher currents, and it tends to take down a lot of things. You got to read about this. This blew me away because I did modeling that was directly related to that, and I actually did simulations directly related to what I'm telling you for underground effects of that on certain systems. And one of them was published with a lot of making everything generic and safe to talk about. All right, now that's sort of that. I hope you can remember this. Currents in the same direction pull together, opposite directions repel. It's a very important concept. Dr. Wood shows some of this. So that's the first one. Now, if you take a look at a loop wire, it's on page 420 or 243. Talk about this. And you know, if you ever do come across anything that verifies what I just talked about, either the power grid in Hawaii or the rails being put together, send me that link, because I thought it was completely classified. But nowadays, classified material is appearing everywhere. Or things that I thought were classified. So let's do this problem. I'm going to ask you. This is a typical kind of problem you get. All right, I got an infinite current I. It's on the z-axis. Now I have a loop. Or I'm going to make it a square loop, like this. Square loop is at a distance d away, and it's got a width a. And on this thing, I got a current, I'll call this I1, and I'm going to have a current I2 flowing this way. Now I want you to hear me so you can understand what I'm talking about. Can everybody follow me in this? All right. Now I want to know the net force on this loop. I want to figure out the net force.
It is square.
Yeah, for now.
Okay.
I'll make it, I'll call this distance d and this height d2. Or, yeah, I'll make this a.
Earlier you made the square A and the distance D.
Yeah, I'll tell you what, I'm going to do this. I'm going to call this distance rho 0, call this A and this A. It won't matter at the end of the day, but that's the current I2 is flowing counterclockwise. Y'all with me? Now, I know that at any distance away, I'll call it rho, that I have a B field going into the board, and the B field is given by mu 0I over 2 pi divided by rho. It'll be going into the board, and if I do my deal here where this is x, this is y, and that's z here, going up, it's going to be minus 8x. I hope you all follow me. That would be the B field, right? Y'all agree with me? All right, let's go through this. So the current's going counterclockwise. Let's take the outer one. What is the net force on this outer one going to be? I'll call it just F1. Call this region 1. Well, the differential force would be IDL crossed into B, right? And then if I multiply that by the height, or by A, I would get the actual force on that member, right? Call this member 1 right here. Right here, call this member 2 here. And this can be 3 here, and this can be 4. You'll see how these two have no contribution in a second. You with me, class? All right, so I want the net force of this one, member 1 here. So that's going to be IDL cross B. Well, I is going up, so it's going to be I2 AZ, I'll call it differential force, crossed into B, B's into the board, which is going to be mu 0, well, just mu for now, over 2 pi. And here, it's going to be rho 0 plus A, right? And that's going to be times I1, and this is in the A minus AX direction. Do y'all follow me what I'm trying to do here? All right. This is the differential force on this member. I2, because that's the current flowing there, is I2. I on purpose made it going counterclockwise. AZ, it's going the AZ direction there. You'll notice here, these two currents are in the same direction, right? This for this element right here. So we know they're going to pull together. At the end of the day, what do you get? I get the differential force on member 1 is going to be equal to simply mu 0 I1 I2 over 2 pi rho 0 plus A. And then it's going to be AZ crossed into AX as AY with a minus sign, minus AY. Y'all follow me? And that would be the differential force. The total force, if that's the differential force on this, pulling this way, the total force would be that times the length, right? Because it's constant. So I can say the total force on member 1 is going to be equal to mu 0 I1 I2 over 2 pi rho plus A, rho not plus A I should say, and it's going to be times the height A and this will be minus a y direction, and that will be newtons, not newtons per meter. What do you think the force is on member 2? Right here. I'm calling that 2, this one.
It's going to be the same in the plus y without a.
Right. He's exactly right. Everything's the same except instead of rho naught plus a, it'll be rho naught, and it'll be in the plus ay direction. So this force is going to be mu 0 I1 I2 a over 2 pi. Here it's just rho naught, and it's going to be ay newtons. Y'all with me? Now take a look at the top and the bottom. I want you to just notice this. Let's go at the bottom. The current's flowing this way, right? We got IDL cross B. The force is upward, differential force. Do y'all see that? Go to the top one. Just take the reference point right above this. Here I got IDL in the opposite direction, right? IDL cross B is downward. Y'all see that? The net amount of force, this is going to be downward, the net amount of force that's going to affect the loop from the bottom and the top part right here will be 0. They'll cancel exactly. Does everybody follow me on this? Y'all see the chase? You good with that? All right, so really the net force on this loop is going to be what? Well, it's going to be repulsive because this one is greater than that. This one is pushing it away. This one is pulling it towards, right? So the net force will be in the AY direction. It will have a magnitude of mu 0 I1 I2 over 2 pi. And then when you look at the actual effects here, I'll put an A here. Now you're going to have that force being equal to 1 over rho naught and minus 1 over rho naught plus A. And that will be the net force. Y'all follow me? Now something to note, you can mess with this all you want. If I want a common denominator, I'll multiply these two. Over here I get rho naught plus A, I get minus rho naught, so it's just A over rho naught times rho naught plus A would be the actual force on that loop. You with me, everyone, class? This is something how you calculate the force of the loop. There's a couple problems he does like that. We have an infinite current, and you put a current loop there. And it will propel it away. One other thing I'm going to tell you, this type of effect, what we're talking about, down here, we have extension cords, right? We have currents in opposite directions. The force is so small, it doesn't rip them apart. Y'all with me? We have extension cords, all right? Current is differential. In other words, it's going this way and then the opposite way. They create magnetic fields, but the force is so small because mu 0 is 10 to the minus, is 4 pi 10 to the minus 7th. And when you do the math on this, the force per meter is trivial. It's almost nothing measurable. 10 to the minus 5th, 10 to the minus 6th, really newtons per meter kind of deal. However, when I was messing with the railgun, when we were building railguns and we had 20, 30, 40, up to 400 kiloamp currents, then if you had wires that were near each other running together, they'd jump and pull together. If they're on opposite, they'd break apart with that level of current. They're very obvious, the force levels. And the one thing I'm just cautioning you on, when you're doing things with electromagnetics, anytime you have large capacitors, discharge a lot of current, try to estimate the peak current values and then calculate the differential forces, because we had wires whipping the way when we were discharging this. I didn't expect that. I never had this secured. It got so bad that we made the, well, it didn't get so bad, the students figured this one out. We had this hollow core, you know that stuff that you make, it was basically a PVC core about this thick. And we had made an inductor. We had to get an inductor to slow the rate of discharge to maximize the amount of energy that these projectiles that we had would get. Well, there's a large magnetic field in the center of that. It's a solenoid. So what these kids figured is, let's see if we throw some soda cans, aluminum soda cans in there that are empty. And they fired that thing into the ceiling like it was a rocket. It was one of those things that it crushed them down and fired it up. I thought, you know, these kids are going to kill me if I don't have their way around here. But I'll never forget that as long as I'm living. I wish we had films of that, or videos of that, because that thing was just... At first, I didn't expect that, put it that way. Anyway, that's just a bit of caution. So now the next force we're going to talk about is on a square loop. Where the thing's going to turn it. This is like the beginnings of an electric motor. Did you guys have your machine, had Dr. Gross for power yet? You had. Well, he probably is big into rotating machinery.
Oh, he is, yeah.
Pardon me?
He'll tell you about it all class.
A lot of this stuff, rotating machinery, kind of, it bridges into mechanical engineering and stuff like this. But most of the stuff, electrical, mechanical, you have to know both to understand this stuff well. All right, so I'm not going to do an entire electric motor, just so you know that DC or AC. But I want to give you an idea of what how magnetic forces cause us to operate. All right, so here is a wire. I'm going to try to draw this the way they want me to draw it. X, Y, and Z. By the way, the thing I just talked about is on page 243 at the top. He does it with the loop, doesn't he? It's easier with a square.
He did it with a square.
He does both. It's a square and a loop.
He's got a loop on 245, but I'm looking for the actual torque and moment. That's on page 247. Let me try to make this clear. So, if we have something like so, this is my coordinate system, and then I go ahead and I put a wire here. By the way, if you get it, well, no, not yet. When you get into EMAG 2, if you get a chance, look up rail guns and coil guns on YouTube. They got great videos about this, and these are kids make these things. They're having a ball with them. Okay, now I'm going to take this and I'm going to put a loop in the XY plane. I'm going to try to at least. So I'm just putting a loop here and assume this thing has A and A, and it's going to have a current I1 flowing around that way. You with me? So it's going like this, looking straight down the Z-axis. It's in the counterclockwise direction. Now, if you look on that for a second, I'm going to put a B field in here, and it's going to cause it to bend. So I'm going to do this, and I want you to watch me. I'm going to put a B field in this direction. So call it B0 AY. I want you to just think about this. We're going to just designate the direction of the forces on this loop. Everybody with me? Let's go out here to this one. We know the differential force is equal to IDL cross B. I put the B field out that way, and that could be from a static magnet or it could be electromagnet. So when I look here, I get IDL going this way, right? Crossed in the B field, can you see that the differential force is down? Y'all with me on that? Don't worry about the magnitude. Now what about the differential force on this member and this member? Look at the equation. It's IDL cross B. IDL cross B. B is in that direction. What is IDL cross B?
0.
It's 0, right? Any two vectors in the same direction cross together are 0. Right? IDL cross B, there ain't nothing to cross it into. It's in the same direction. Follow me on that? So no force here and here. What about the force on this one?
It'd be up in
Exactly.
opposite magnitude.
This would be the differential force. Same magnitude, opposite direction. Y'all with me? Now, there's something called torque. Y'all remember torque in physics? So what torque is about a point, if this is a point that's called an anchor point, and I have something of length L around it, and you should do this with vectors, but I'm not going to, and I put a force down here, F, it creates a torque around here. And I'm going to make L a vector and F a vector. And it causes a torque here, and torque is equal to L cross F. Y'all remember that?
Yes.
Now, just to be clear about this, if you use your right hand, and you want to know the direction of torque, it's L cross F is into the board. So the torque would be into the board, and it would cause it to rotate this way if allowed to rotate. That should be obvious. Do you agree with this, class? You with me, Chase? All right, come back over here. When I look at this one, I'm going to look down the x-axis. So if I just look at this, I'm going down the x-axis. This is y, and this is z. I'm out a distance. If that's a, this distance is a over 2, right? That would be from here to here. Do you all see this? Now I know there's a force out here pushing down. That force pushing down would be the length A times, it's really IDL crossed into B. Well, it's when you do the integration, it's going to be I times L times B. Do you all agree with that? Pushing down right here. You all agree?
Mm-hmm.
I feel the same way. All right, so this force is equal to I, L, and it's going to be IA in this case because I made it IA times B, right? Now, do you agree that there's the same exact force in the opposite direction equal in that thing, and it's causing the thing to rotate in the same direction? Do you all agree with that? That means the actual torque here would be equal to 2 times the actual torque on 1. So it's really simply equal to this vector direction, which is going to be 11 arm of, I'll just write it down so you can see it. It's going to be A over 2, and I have that in the y direction, AY, crossed into the forces downwards, so it's going to be IA times the B field, A minus AZ, and that would be the torque from 1, since there's 2, it's times 2. And that means the torque is going to be equal to I A squared times B. You can put B naught here if you want. And then I get AY crossed minus AZ. Well, AY crossed AZ is AX. With a minus sign, it's minus AX, or it's into the board. Torque is going into the board. And this would be the actual torque for this thing. You all see this? Now, something I'm going to mention. Oftentimes when they talk about torque, that's the torque. This is the peak torque. If this thing's allowed to rotate, it's going to rotate, right? Well, what happens when it rotates by 90 degrees and the actual loop is like this? Now, the B field's that way, right? We still have a current going this way and a current going this way. But just think about it for a second. It's going to become very clear. Well, what's the torque on this one? I mean, or the force on this one? We got IDL cross B, right? IDL cross, it's downward. You all see that? What about the bottom one? IDL upward, right? What about the two end ones?
They're both inward against each other.
It's 0. The net torque is 0, the net force is 0. Now that's called the place it wants to come to rest at if allowed. All right? Y'all with me on this, class? So, what actually happens with this? This loop, when it's in this state, has a maximum amount of torque, and then it will move and basically oscillate around it. There's got to be some damping that comes to this position if nothing changes. Do y'all follow? Now here's how an electric motor works. There's a couple of tricks to this. I'm going to make this, I'm just going to tell you the real way a electric motor works. It's going to be a DC motor. An AC motor, it's different for a DC. Normally they don't have one wire, they have a whole bunch. So when they have a loop of wire, they'll have something like this. Whole bunch, and each one of these, this has a current I with a whole lot of turns, right? Now they'll put a B field here created by something on the outside portion called a stator. Y'all remember this? It's something where there's going to be a way where there's a whole bunch of small coils that can create a magnetic field in any direction you want. It's there. When this loop, all right, has no, if you take a look at the differential surface, when the differential surface of the loop dotted into the B field is 0, it's a maximum torque. All right, so this thing wants to rotate. If you think about this, IDL, if you look just here, IDL going in cross B, it's going this way, and then this way. So if it moves a little, when it comes down here, moves a little bit, then what they do is move the B field. So the B field's in this direction. All right? And these are from the outside coils. Isn't that how we explain it in power? That what you're doing is you're energizing, you're putting current in these outside coils that create a B field. So now the thing moves a little bit farther, and you keep varying that B field where it is, so the thing will just spin at the velocity you want. That's an AC motor, and it has very large torques, typically. Now, did he go through DC motors?
He did, yeah.
DC motors, there's a couple ways to make them, but generally speaking, what they do is they're going to change the direction of current on this inner loop, and they'll let it rotate. I'm not going to get into all this stuff. You guys are going to, if you haven't had power, you're going to get it, but that's the essence of it. It's based on magnetic forces. I want to say one other thing about this. Rotating machinery is something I'm not an expert in, but I know enough. AC motors don't blow up. DC motors can. If a DC motor doesn't have a load, it's something's not being driven by it. A regular DC motor without any load on it can blow up. Did Gross go into that, Dr.? And literally, the thing will just keep rotating and rotating. Either the bearings will burn out and force it to stop, or the inside part, the rotor, will just blow up like a grenade. And I've never seen it happen. I don't want to, but I know it does happen. It's a dangerous thing. So if you got DC motors, make sure you always have a load on it. There's probably a fail-safe, so you can't run without a load. But I don't know enough about that. That's sort of, in a nutshell, when you do some problems, you're going to see that's the way it's done. They talk about torque is equal to what's called the magnetic moment of the loop crossed in the B field. I'm almost out of time. This is on page 249. I'm going to give you some problems and go through this. Then I'm going to go through permanent magnet stuff on Monday, and we end this course at the end of the month, I think. It's the last lecture, so I don't want to talk, but I want to get through magnetic materials, and we'll talk about boundary conditions. So would you do me a favor? Can you empty that row, fill this row up? All right, so right where you are. I'm doing it just the way I did in the first class. Then empty this row, fill this row up where the camera is, empty that row, and fill the other row. It doesn't matter where you sit. I hope that, do you understand this lecture? Because the information